Hello there, Honda here, and in this video we're going to be discussing the acceleration in EVE Online, how this might be calculated, and how various modules such as armor plates and different things like that might affect your acceleration. So the first thing to know about EVE Online is the things that you may have learned in your high school physics, like F equals ma, the Suvat formulae like v squared equals u squared plus 2a, all these different kind of formulas, they are perfectly valid for real life. That's just classical mechanics. And this game, the game doesn't work on classical mechanics at all. We have an entirely different system. So for example, if I look at my stiletto here, we're moving in space, and it's supposed to be a frictionless kind of area. And yet if I stop my ship, if there's no friction, then the ship shouldn't decelerate even though I turn my thrusters off, or if it does decelerate, then there should be a force going in the opposite direction to slow it down. Now we don't see that here, and again that's because the game doesn't work like that. The way that the game does work is more based on imagining that you're submerged in a fluid. So I think the most relatable way that you can understand how this game works with acceleration is, imagine you're in a swimming pool. So we've all been in a swimming pool, or most of us have, or in the ocean or such, and we've all experienced that when we try and, for example, punch through the water, it's quite difficult to do when we try and do that quickly, so we move our hand very fast. You feel a lot of force dragging you back there, whereas if you move your hand slowly through the water, not so much. Okay, it's actually fairly easy. You don't feel much resistance at all, and you can kind of just glide your hand along the water. Okay, so there's a very similar principle here. So if I stop my ship, you're just imagining that you've got nothing going forward. It's like a submarine almost, where you turn imagine this is like a submarine, you turn your propeller off, you're going to slowly kind of slow down to a full stop. So if we open up our fitting window for the ship, we can take a look at the two values which acceleration is affected by. Now the first one here is right there, inertia modifier. So the idea here is that the lower this value is, the better off you are. This is essentially affecting how well your ship, well it says it there, how well your ship turns essentially, okay? How tight of a circle can you do on an orbit, how fast can you align, etc. And the second one you can get from show info by going to attributes. The second one is the mass. Go away downtime. The second one is the mass, okay? Now acceleration also is affected by the maximum velocity of your ship. So if I, for example, turn this micro warp drive on, I'm going from very low speed to a very high speed. Click this micro warp drive. You notice that at the initial burn, very fast getting from there to there. Then look, as it gets closer and closer and closer to my maximum velocity, it is slowing down. And then when I get to the extremities of this burn, when I'm trying to get to 686 there at the end there, look how long it's taking for those final few points. 5 and 6. There you go. So it took a very long time. Okay. Now we're going to be able to see that graphically later on, but that's the idea. And the same applies for the deceleration. If I turn this micro warp drive off, there we go, then you're going to see that the initial deceleration is very sharp, but as it approaches its new maximum velocity, 644, we're slowing down. So now let's have a look at the actual equation which is used by the game's engine in order to calculate how fast an object would be moving after a given time. Okay, which is of course based on acceleration, because acceleration is the rate of change of the velocity. Now the formula goes like this. We have the velocity after a given time t, that could be in seconds. In fact, we will use seconds because the speed is meters per second, right? Now this will equal the maximum velocity, which we'll call v max, multiplied by, big bracket here, 1 minus the exponential function to the power of minus t. So if you have 2 seconds, you need to put minus 2 there, for example, divided by the inertial modifier, which we looked at before, multiplied by the mass in kilograms. Now, this isn't quite the end of the story. We actually require the mass to be divided by 1,000,000. So, for example, if you have 2 million kilograms mass, we'd want it times by 2, not 2,000,000. Really easy way of doing that, if we simply multiply this value here by times 10 to the 6, then this times 10 to the 6 would cancel 6 of the zeros on the bottom there. Or another way of thinking about that is, if you take the mass and multiply that by times 10 to the minus 6, oh, let me get rid of that bracket, then, well, I've just moved this down here, right, by the exponent rules, but anyway, you get the idea. We want this to be divided by 1,000,000, so either way achieves that. I'm going to rewrite this a little bit differently though. I'm going to change this here, because that can get a little bit messy, to this. So then I'm just using the exponential function written in that form instead of e to the and then that fraction. And I think this one here will be, a little bit easier to deal with. So let's look at an example of this. So if we go back to my stiletto that I showed you at the very beginning, my stiletto's maximum velocity with the micro drive off was exactly this, 644.57 meters per second. Its mass was this, inertial modifier was that. Okay. Now, these three values here, if we remember, are the only three values which you need to use in order to find out various accelerations and final velocities and whatnot. And what I'm interested in is how fast would that stiletto move after exactly 2 seconds, assuming that it's starting from 0 speed and then it begins accelerating. Okay, so let's work that one out. So we're going to use this formula here. So plugging these numbers in, we're going to get v of 2, so that's how fast it moves after 2 seconds, place that t there, equals v max, which was this, 644.57, multiplied by, big bracket here, 1 minus the exponential function of minus t, so that's minus 2, times 10 to the 6, over the inertial modifier multiplied by the mass. So that's going to be 1.7179 multiplied by that mass, which is this huge number here, 1,010,000. Close the bracket for the exponential, close the bracket because for the Vmax multiplying there, and extend this fraction line. And let's put that in a calculator. So you can see here that the final answer, when you put this into a calculator, will be 441.02, which, I mean, it's 0.02, yeah, right. I'm gonna round that up to just 441, okay? So that will be then V after 2 seconds of this stiletto with these numbers, assuming you're starting from 0 speed, equals 441 meters per second. So now let's say we're interested in a different thing. Let's say we're interested in how long would it take for an object to reach a given speed in Eve, okay? And that can be useful actually, for a couple of reasons. The first might be you could use that to find out how long it takes for you to enter warp, which we'll look at a little bit later, or it could be how long it takes to reach your maximum speed, which is actually a little bit more interesting than you might think it is. But I'm going to rearrange this equation now so that we get it for time. So here's our new formula. Let me just modify this a little bit. I'll get rid of this implies sign because we're not really, we'll just take this as a separate formula now. And I'm going to put a little subscript v there to mark that that's the time that it takes to reach that velocity. So you can see that the time is take the negative of the inertial modifier multiplied by the mass, multiplied by that 10 to the minus 6, which again divides the mass by 1,000,000, multiplied by the natural log of 1 minus the speed that you're interested in over v max, the maximum velocity. So taking an example here, let's find out again with our stiletto with the same information, how long will it take for my stiletto to reach 500 meters per second. So we're going to have time with velocity 500 equals minus 1.7179 multiplied by the mass, which is 1,010,000. You could put divided by a million. Yeah, I think I'm going to just change that a little bit actually. I'm going to put this over 10 to the 6, just dividing it by a million. Then multiply this by the natural log of 1 minus the speed you're interested in, which is 500, over the maximum speed, which is 644.57. Put that into the calculator and we see that it will take 2.59 seconds. And that makes sense to us because if we remember the previous example, after 2 seconds it reached, I think it was, 441 meters per second. So to reach 500, we did expect it to be a little bit above 2, which this is. Now that we've looked at the actual equation which is used in the game's engine, we can actually use pyfa to streamline this process so that we don't actually have to sit with pen and paper or whatever it may be and calculate these values. pyfa actually has an inbuilt function for this. So if you open up the fit which you're interested in, I've got my stiletto here, and I go up to the top left, I click fit, then I click graphs, and then here I change this damage stats to mobility, and here I get the exact same thing, just as a graphical representation of all values evaluated along that function. So for example, we took our example that in order to reach 500, I think it was like 2.6 seconds we've calculated. So let's verify that. So if we move this to 500, that's as close as I'm going to get it, I think. There we go. Then indeed, we see that we get 2.6 seconds. Now, this graph I'm going to use just to go into my next part of the video. Let me just expand this actually. So when we go up here to the extremities there, so there's my max speed, but you know, assuming that the micro driver is off, there's my max speed. Of course, after a while it doesn't increase any further no matter how far along you go on time. But if we look at like from here to like there, you're taking like 4 seconds roughly to get an extra 20 meters or even 10 meters per second there, which makes sense. So it's a rapidly increasing function. Okay, now I did mention a little bit earlier that this equation is actually a little bit interesting because when you take the natural log, because as some of you may be aware, you can't actually evaluate the natural log of 0. We're going to look at that a little bit later, but for now I just want to just kind of keep this in mind that when you get up here, the equation doesn't actually get followed to the letter when you get to the extremities, the very highest end, at the very final stages of an acceleration. The game tends to do round values up after a certain point. So after you might get like from say to about 640, to get from 640 to 600 and the max speed, in theory, it should not be possible for you to reach the max speed with the equation which is used in the game's engine, because you can't actually evaluate the natural log of 0, which again we're going to see later. So in theory this isn't possible. In reality it actually is possible. So what happens is after a certain point, the game just rounds up and says, right, now you're travelling at max speed. So let's see the mathematics behind what I'm talking about there. So if we look at this time formula again, let's say in this case what I'm interested in finding is how long does it take for my ship to reach its maximum velocity, okay? So that would mean that this term here, which is the term that I'm looking for, would be Vmax, right? You're plugging that value in and then doing all this work to find it out, okay? Now, this stuff here at the start, it just ends up being a constant, so we're going to just ignore that. This ln function is really what's guiding this. So I'm just going to take this over here, and let's see what happens when we plug in Vmax here. So that could be a general Vmax for any ship. So that would then equal ln of 1 minus Vmax over Vmax. And of course, when you have this situation, when you have the same thing divided by itself, that's just 1. So that would be equal to ln of 1 minus 1, which is ln of 0, and that's what I'm talking about. Now, we can't evaluate this, okay? What power on e makes 0? None of them, right? For those of you who aren't familiar with what the log function looks like, this is the natural log of x I've just put into Desmos here, and you can see graphically what I'm talking about. So there's 0 there, and we can get close to 0, and eventually it will look like, well, it's at 0, but but then you scroll in and you see it's not at 0, and it will never actually in theory reach 0, even though that's required for our formula to reach Vmax. So again, just to reiterate that after a certain point close to Vmax, the game no longer says, well, okay, you need an infinite amount of time to reach your max velocity. It will just eventually round it up and say, okay, now you're at max speed. So using this formula, what we're also able to actually calculate is how long it takes for us to enter warp in a given direction. So the requirement for a ship to enter warp in EVE is that you must be travelling at 75% of your maximum speed in the direction that you want to warp in. So we can first of all take our maximum value here, 644, and multiply this by 0.75, which is the same thing as 75%, and this will equal 483.43, rounded to 2 decimal places, meters per second. So my stiletto with my micro warp drive off must be travelling at this speed, 483.43 meters per second, in order to enter warp. So if I then use this formula with this value as the velocity that I'm interested in finding, I can then find out what my align time is going to be. So there we have it. I plug those values in. You can see here at this point I've basically just written the 0.75 times the max velocity so that I can do this all in the one line and not have to take 2 calculations, but I've now found that it would take me 2.41, so round that to 2 decimal places, 2.41 seconds in order to enter warp. And just keep in mind we have to be careful, there were server ticks, so in reality what that really means is 3 seconds. Just to double check this and make sure that we're doing the correct thing here, we can always go back in the game and check out our ship. So if I look at my stiletto and open the fitting window, indeed I get 2.41 seconds on the align time. So what I would like to look at now are a few modules in the game which will affect our acceleration. So I'm only going to take a few examples here. These are the most common ones that I see off the top of my head. There may be others, there probably will be others, but you know, micro warp drives, armor plates, nanos, inert stabs, all these things are fairly common. I think, you know, most people watching this video will probably already know how these modules affect their ship. What I'm more interested in is why would they affect the acceleration, you know, specifically the acceleration. So let's take a look, for example, at the micro warp drive. In fact, I'm actually just going to use my own ship as an example here. So if I open up my fitting window, we see that with my micro warp drive off, my weight, or sorry, my mass is, well, that's just the number divided by 1,000, but it's, you know, it's 1,010,000 kilograms. If I turn my micro warp drive on, however, you notice my mass goes up by 500,000 kilograms, or in this case 500 tons. So what's going on there? Well, if I right click and show info on my micro warp drive, I can see in the attributes page, mass addition 500,000 kilograms. Okay, so that affects our acceleration, and as we've discussed before, that the higher the number that the mass is, the lower your acceleration is going to be. Similar with inertia modifier, but there's nothing here, well, as far as the micro warp drive is concerned, there's nothing which affects the inertia modifier, whether it's on or off. Now, you may be thinking at that point, well, that doesn't seem true, because when you turn your micro warp drive on, you seem to go way faster, and your acceleration, certainly at the start as well, is way faster. And that's correct, but also keep in mind that we have that other part of the equation, Vmax. So yes, your masses went up, which would in theory reduce your acceleration, but then Vmax is increased by 4,000 meters per second, which is a huge increase, so your acceleration overall will increase. So let's simulate my fit here. So here's my fit, and if I simulate this, let's try and put on some modules here, and we'll mess around with this and see what happens. So let me just turn this micro warp drive off, and let's add, for example, a 400mm plate for some whatever god awful reason. So if I add a 400mm plate on here, which, there we go, then we can see here it doesn't fit, but that's not the point. It also increases my mass, and that makes sense. If I show info, I get again a mass addition. So when you add armor plates to your ship, your acceleration is going to be slower. And also the strings that make it faster. So you may have noticed that when I removed my nano there, my inertial modifier went up, which is what you don't want, right, for an acceleration. When I put that nanofiber back on there, my inertial modifier goes down. And then that would make sense, because if you look at the attributes, the modifier there is inertial modifier takes minus 15.75% off, at least for the first one. This does have stacking penalties, do keep that in mind. And then if you take an inertial stabilizer, well, it's in the name, right? This one exclusively focuses on inertia modifier. So if we take these, so we're at 1.7179. If I take my 2 nanos off and put them with inertial stabilizers, we will get a value which is lower than that, but you also have to keep in mind then that you don't benefit from also the speed increase that you get. There's velocity modifier there that you get from the nano. So that's why I tend to stick with the nanos instead. The very final thing that I would like to look at in this video is a little cautionary advice on reading your inertial modifier number correctly. So as I mentioned before, if I look at my fitting window for my stiletto, the lower that this number is, this inertia modifier, the better off your acceleration is, because when you multiply the mass with the inertia modifier, this gives you what is known as your agility in Eve. Okay, and essentially the lower the number of the agility you have, the better off you are. Now if I switch ship to, let's say, a battleship, so I've got, for example, my Sin here, if I look at this, my inertial modifier for the Sin is actually significantly lower than the stiletto is, right? And you may think, well, okay, but haunting, triple plated Sin does not align or accelerate as fast as the stiletto does, and you're absolutely correct in that. What's actually going on there is the amount by which the mass of the ship, so you see here, the mass of the Sin is, where are we, is 148, nearly 149 million kilograms, which is nearly 149 times more mass than that stiletto is. The amount by which that mass has increased is way more than how much the inertial modifier has decreased. So in the end, when you multiply these two numbers together, in comparison to when I take the stiletto, when you multiply these two numbers together, this number here for the stiletto will still be way lower than the two numbers that you multiply for the Sin together. So the respective agilities will differ in favour of the stiletto. In any case, with that is my conclusion to this video. I do hope that you found it useful and informative. This is the first video in this series, and of course this is a completely new format for me. I'm kind of making it up as I go along, if I'm being completely honest with you. If you do have any suggestions on how to improve such videos, because there are going to be more that will be released, periodically, please do comment down below and let me know how you might have found this video more interesting, more useful, more informative. Otherwise, thank you and take care.